As we expand our skills in counting problems, the first thing we're going to talk about are permutations. Permutations focus on counting in situations where order matters. That's probably the easiest way to think about this. And you can think of a permutation as a specific arrangement of what you're interested in. So one of the things we're going to need to understand when we're dealing with permutations is the idea of a factorial. We've already seen factorials come up. We just didn't write them that way. So a factorial is when you write out a number multiplied by numbers one smaller and one smaller. So for example, 3 factorial is 3 times 2 times 1. And I can show you what 4 factorial would look like. 4 factorial would be 4 times 3 times 2 times 1. And so anytime I'm counting things with specific order, if you think back to the multiplication rule, I end up doing something like this. So for example, if I was to say, how many 4-digit codes are there if there's no repeats and you only have, say, 10 digits to choose from, you would be counting down. Now, this isn't exactly a factorial, but it's the exact same idea, right? So both of these are illustrations of a type of permutation. Factorials apply to a specific type, but mathematically, you'll see factorials pop up all over the place. And so anytime we have a set of exactly n things and we want to arrange them, we can use n factorial. Here, if I wanted to arrange all 10 numbers, if I wanted to know how many arrangements are there of 10 numbers, 10 single-digit numbers, that's including 0, right? I would say 10 factorial. This right here is not 10 factorial because it doesn't count all the way down to 1. So permutations are based on factorials mathematically, but that's not the only way that you'll see permutations. So we'll just jump right into an example, and then we'll jump into other examples where you can see how these work. And so we'll look at this in 2 different ways. So it says, let's suppose we wish to arrange 5 paintings from left to right on a wall. So that tells you order matters, right? If the first painting is different, then it's a different arrangement of paintings. How many ways is this possible? So method 1 uses the multiplication rule. So I say, okay, I imagine there's 5 spots on the wall. And so for the first spot, I can imagine I have 5 choices for that spot, right? For the next spot, I now only have 4 choices because I've already hung one of them up, and so on, right? Okay, well, the other method is to actually apply what we just talked about. By definition, the number of ways to arrange 5 objects would be 5 factorial. Now, mathematically, these are identical, 100% identical. But the idea behind how we chose them is a little bit different. And on your calculator, to do this, you would just type the 5 and then press math. And if you go over to the probability menu, it's either called PROB or PRB. You'll see a factorial as number 4, and you can then press that and enter. And for this one, you'll get 120. You can also do factorial on Excel or on Wolfram Alpha. So both of these methods are counting the same thing. Mathematically, they're identical, but the way we thought about them is a little bit different. But you can see that in general, using factorials is based on the same idea as the multiplication rule. So another example that's a little more complex, it says, okay, in how many ways can 3 girls and 4 boys be lined up for a picture? Now that lined up for a picture part, remember, all of this is about order mattering. And so lining people up for a picture definitely makes order matter. And not only that, we want the girls to be on the left and the boys on the right. So instead of thinking of this with 2 different methods, although we could, let's try to apply factorials. But in the end, we're going to have to think about the multiplication rule a little bit because of this aspect right here. Girls on the left, boys on the right. So the multiplication rule part, we could say, okay, this is the number of arrangements for the girls. And then, so it's times, number of arrangements for the boys. Right? So I say, okay, what's the big picture here? I'm arranging the girls in a line, I'm arranging the boys in a line. How many ways are there to arrange the girls? Whereas there's 3 of them, and every arrangement is different order matter, so this would be 3 factorial. And then it's times, how many boys are there? 4, so there's 4 factorial ways to arrange them. And so 3 factorial times 4 factorial, if you check on your calculator, is 144. So you notice when we're counting where order matters, we're getting rather large numbers. I mean, okay, 144 isn't the biggest number ever, but if you think about it for the idea here where we only have 7 people in this picture, 144 different possible pictures is pretty significant. And again, it's all because every time you move one person in a different spot, you essentially have a different picture. It's all about that order mattering. So this is when you're actually arranging all elements in a set. That will not always be the case. So if we go back to example 1, that was where we were dealing with the paintings. we might have 10 paintings to choose from and we only want to arrange 5 of them. That's kind of like the first question I said, where I said, okay, what if we had a 4-digit code and we have 10 digits to choose from? And order matters, of course, and we're counting down. And so in a way, what you're doing is you're counting down, but you're not using all of the numbers. If I wanted to answer this question using the multiplication rule, I'd say, well, I got my 5 spots now, but for the first painting, I have 10 choices. And for the second painting, I have 9 choices, etc., right? So I count down, but I don't end up using all of the numbers. So as you can see, though, how many did I count down by? 1, 2, 3, 4, 5. So essentially what I'm doing is I'm arranging 5 things out of 10. And so the way we actually write this down, this isn't factorial anymore. This is a permutation, and it's called permutation of 10 objects taken 5 at a time. I know I have that written down here, but I wanted you to see what it meant. So it means that out of 10, you're arranging 5 things. And if you were to simplify this has a complex formula that you can see down here. But if you simplify it, it will actually look like the multiplication rule right here. Mathematically, they're identical. Now, you don't need to know this formula. I provide it here just because it's one of those things that we learn about. This is also built into your calculator, and the way you have to use it on the calculator is you have to type the first number. So I type 10, then I press math, I go to probability, and then I press number 2 permutation, and then I'm giving a spot to put in the 5, and I can press enter. So by the way, for this, in case you're curious, this is a humongous number for this situation. You might be surprised to know. It's huge. So 30,240. And so again, we have a ton of arrangements because we have 10 paintings to choose from, and every time you use a different painting, and every order is considered different. Order matters. Of course, remember, the ultimate goal is to eventually do probability, and we need to be able to count. And so we're considering essentially all the possibilities. So let's see a couple of examples with this. One of the most common situations you'll see to imply order matters is by giving the spots and who we're choosing names. So what I mean by that is, imagine we're picking a president, VP, and secretary for an organization. Picking Tom as the president versus Tom as vice president, that's person having each role is different, right? So naturally order matters. So that's what I mean. A classic problem would be giving names to the spots so that order matters, and that's something you got to pay attention to as a pattern. So this right here, since we're picking 3 things, order matters, and we got a total of 32, so we're arranging 3 people out of 32. So this would be a permutation of 32 taken 3 at a time. And so when I calculate this, I end up with 29,760. Again, a large number, but it's considering all the different ways you could arrange the 3 as well as pick the 3. All right, so that's probably the most straightforward type of permutation problem that you'll see. In some cases, what you're going to have to do is combine rules that we've used before into rules like the permutation. And we sort of saw this when we were dealing with the girl-boy school picture problem. So in this example, a club has 25 members and 12 pledges. So essentially, we got 2 different groups. A president, VP, and secretary are selected from the members, and that's very important, and a pledge chairman and a pledge vice chairman are selected from the pledges. So remember, and is kind of related to intersections, which means multiplication, and ors are kind of related to unions, which would mean addition. So and is important. Both of these things are happening. And so now what we want to know is how many ways could the 5 officers be selected? So again, what are the 2 steps? We're going to pick the VP, etc., for the members, and so multiplication, and we're going to pick from the pledges for whatever they got. All right, so let's consider just the members first. Because these people that we're picking have labels on them, president, VP, etc., order matters, and there's 25 and we're picking 3. So order matters, so it's permutation, 25, 3. And so I multiply. Now the pledge chairman, pledge vice chairman, if I'm hired as a pledge chairman, it's very different than vice chairman, so order matters. There's 12 to pick from, and we're picking 2. So again, notice what I did. I applied the multiplication rule, but I also applied permutations here. So let's calculate this and see what we get. A humongous number, by the way. 1,821,600. So I'm hoping you're practicing on the calculator, double checking this. I get about 1.8 million different ways. So again, it comes down to that order mattering causing all this. So this by itself seems pretty straightforward, right? As long as you pay attention to whether order matters or not. And so what we'll see next in the next video is, what if order doesn't matter? What do we use then? And then eventually we'll tie it together with all kinds of situations where we could end up using any of the counting rules that we have.